In the previous theorem, we proved the main part of the correspondence theorem, which basically had the following kind of things. We let R be a ring, and I is an ideal of R. So let me write down in my picture over here that I is an ideal. And the main result in the correspondence theorem says that if I have a subring up here in R that contains I, it corresponds to the subring S mod I in the quotient ring R mod I. And the critical part of the proof was that we let pi be the natural or canonical map from R to R mod I. And under that map, S mod I turned out to be the image of S. The correspondence theorem goes on to state that S is an ideal in the ring R if and only if S mod I is an ideal in the quotient ring R mod I. And that's what I want to prove in this particular video. Now, I want to start with the definition of ideal. So let's go back and remember the definition of ideal. The definition of ideal says the following. S is an ideal of the ring R if and only if, well, first of all, S is a subring of R, and for every R inside the ring R and every S inside the subring S, we have that both R times S belongs to S and we have S times R belongs to S. Now, we also need to be thinking in terms of what the definition of ideal means for this particular subring of the quotient ring R mod I. So let's also get that written down. So let's also make the note that S mod I is going to be an ideal of R mod I if and only if, first of all, S mod I is a subring of R, and for every element inside the quotient ring R mod I, now all of those guys would look like for every R plus I inside R mod I, and let's see, the elements of S mod I are cosets of I with representatives in S, so for every S plus I living inside the ring S mod I, we have, let's see, R plus I times S plus I has to be inside S mod I, and we need S plus I times R plus I to be inside S mod I. And what we want to do is we want to show that these two things are equivalent to each other under the stuff that we know from the correspondence theorem. So let's think about what we have. We already know. We know that S containing I is a subring of the ring R if and only if S mod I is a subring of the ring R mod I. We already did that from the previous video. So all we have to do is show the additional properties for ideals also behave in an if and only if fashion. So let's look at this. S itself is an ideal in R if and only if we have two things. For all R inside R and all S inside S, RS has to be, let's make my notation correct, RS has to be inside S, and SR has to be inside S. But this statement here will be true if and only if we have, for every R inside R and every S inside S, pi of RS has to belong to pi of the subring S, and pi is the canonical map, remember. And likewise, pi of SR has to belong to pi of capital S. And this is just the way ring homomorphisms work. But now we're going to actually get into the idea of what does pi do to these two elements. So what we now have is that this step here is true if and only if, for every R inside R and every S inside S, we have RS plus I has to be inside S mod I, and we have to have SR plus I has to belong to S mod I. And I kind of want to put some reasons down on this one. We know this for the following things. We know this by the definition of the canonical map pi going from R to R mod I, and we also know this from the fact that the first part of the correspondence theorem said that pi of S is indeed equal to S mod I, and that was in our previous video. So now what I want to do is I want to think about something else. This is just a coset multiplication in a quotient ring, because we know that S mod I is a subring. And this is a coset multiplication inside a quotient ring because we know S mod I is a subring of R mod I. So we can continue with our symbol manipulation, and we can say that this step up here is true if and only if, for every R inside R and every S inside S, R plus I times S plus I has to be inside S mod I, and S plus I times R plus I has to be inside S mod I. And this is basically by the definition of coset multiplication in the subring S mod I. But what this is now saying, since I already know, and I want to kind of make some notes here, this guy here is in S mod I, and he is an arbitrary element of S mod I because S up here is an arbitrary element of the subring S. And we also have R plus I on both of these. That is just a random arbitrary element of R mod I, because R is just been chosen to be an arbitrary element of the ring R. In other words, we can rewrite this last statement here as follows. We can think about this last statement here as being true if and only if, for every R plus I inside the quotient ring R mod I, and every S plus I inside the quotient ring S mod I, we have R plus I times S plus I belongs to S mod I, and we have S plus I times R plus I belongs to S mod I. But this last statement is exactly the same as saying that S mod I is an ideal inside the quotient ring R mod I. And so when we put this all together, we have to box some stuff in. S is an ideal in R if and only if S mod I is an ideal in R mod I. And so to tie this up, we are now entitled to say that S is an ideal of R that contains the ideal I if and only if S mod I is an ideal of the quotient ring R mod I. So the correspondence theorem says subrings in R correspond to subrings in R mod I, and ideals in R correspond to ideals in R mod I. In other words, let's take the time to redraw the picture one more time and state the result very clearly. So if we have a ring up here, and it contains a subring, rather an ideal down here, and we do the natural map pi to R mod I, the zero ideal in R mod I will be pi of I, and the correspondence will send subrings to subrings, and it will send, let's see, here's a pretty color, ideals into ideals. And that's the full picture for the correspondence theorem.